Absolut.
Das ist schon ein krasses Problem. Everybody is here? Think so? Perfect. So, then we come to the next talk in our session where we might learn why the flickering is not annoying in the target scenario.
Yeah.
And the presenter will be Gabriel Cavallo. So,
Thank you. Thank you. That was nice. Like when you made the question, I was like, oh, that's nice. I'm going to talk about it. So. Okay, so I'm Gabriel. I'm going to talk about the article on the development of a perceptual model for eccentricity dependent spatial temporal flicker fusion for video graphics. Quite a long term, but yeah, we understand it. There are the others. Right, so the outline for this presentation is divided as follows. We will begin with a quick introduction and the presentation of the motivation that made the authors decide to write this thesis, followed by the understanding of the main concepts that surrounds the topic. Further on, we'll see the methods that they use, how they proceed to make the experiments, and the results they gather from this data analysis. And finally, we will conclude what they got from all this work and all they did, and how important is this work in the field. So, the context of the development of this article includes the development of VR and AR systems, so virtual reality and augmented reality systems, which are ever and ever more words. They're getting more known and of course more interesting with time. They allow us to experience games in a more interesting way, for example, but they promise to also be used in many other applications, for example, medical applications, maybe one day. However, the problem, the challenge to do, to make it more available and accessible are the technical demands. Because to produce a VR systems, it's very hardware and bandwidth demanding. It's a very heavy computer intensive workload. So for this, for video graphics techniques have been developed for quite some time now to make this better, to optimize those methods on how to render image for this kind of system. We understand this a little bit more in detail, what video graphics mean. But for now, we just have to understand that in this context of the hardware limitations and the need for optimization, those techniques are developed, and the unique aspect of the article itself is that inside this broad context of a video graphics, it accounts for spatial temporal aspects of human vision, which is something that has been quite overlooked by other techniques so far. So the goals and the contributions that the authors aim to get were to design a model that could help them understand how which thresholds of the human vision would allow us to save bandwidth, which is something we'll further understand better. But yeah. Also, they wanted to find the fit the several data and understand and extrapolate the model so they could make other I'm sorry? Predictions. Thank you, yeah. For the predictions in the field. And of course, analyze the bandwidth considerations and see how this new model would help to save on bandwidth. All right, so a quick biology class review, very quick. Basically, this is the human eye anatomy, and right behind, let's use this. Right behind here in the eye, we have the fovea, which is region in the eye, the human eye, where we have a high concentration of cones. and it's where the images are then formed to be understood by the brain. So that's basically where the image is formed. And here is from where the term foveated graphics comes. Foveated comes from fovea, so basically foveated graphics are techniques that take in consideration how the fovea works. All right, so now understand the main concepts related to basically the title of the article, which will help us understand the context as a whole and what's the thesis itself. So first of all, what's a perception model? A perception model is basically a model that represents how the human vision system works. Eccentricity dependent is a very cool term to basically express something much more simpler than the word itself, which is eccentricity refers to the distance from the center of a circle or a radial shape, in this case the fovea, or the back of the eye, until where the light is actually reaching. So basically what it says that this model is going to consider how far from the center the light is reaching, and that is going to be used for the analysis. Spatiotemporal refers to the fact that this model takes into account spatial aspects and also temporal aspects of the human mind, the human vision, sorry. So for the spatial part, we already know is the eccentricity, so it's how distance and spatially the light reaches in the eye from the center of the fovea. And the temporal aspect is the flicker fusion, or the flickering in the eye. The flickering is basically the phenomena that happens in the vision, which is the rapid alternation of bright and dark stimuli. And the flicker fusion, the fusion is when this alternation is rapid enough that it cannot be perceived. The change in dark and bright stimuli cannot be perceived, so it seems like a one thing. So it's like if you take like old movies and you had like those images passing by, what they did to come up with like cinema and movie is make those images change fast enough so you don't notice that there are cuts in the movies. So that's basically the idea behind flicker fusion. Computer graphics, as we talked before, are computer graphic techniques for rendering that considers how the fovea works, so it takes in consideration flicker fusion, eccentricity, and everything else. And gaze contingent graphics, as an honorable mention here, is basically a specific kind of computer techniques that take into account the movement of the eye. All right, so for the methods, they developed a prototype display, a custom prototype display, which basically consisted of the DOP, which is a dynamic light projector. Yeah, dynamic light projector. The LND filter, which is basically a filter for the light that comes from the DOP, and it helps to provide the user with safe levels of brightness, so it doesn't harm your eyes. And here's the diffuser, which will work basically as a projector. So instead of having as if it was like a screen directly to the eye, you have this whole system. So the image is produced here, shown here, and comes to the diffuser where the user will see it. And from this prototype, also some assumptions were made. Basically, three assumptions were made. They considered equal sensitivity for both eyes, so this way they could measure only one of them. They also consider sensitivity. The sensitivity is rotationally symmetric around the fovea. So if you imagine the fovea like as a circle, if you look at up front, basically we can consider like not as an ellipse, but like as a circle, indeed. And finally, they also consider that sensitivity is rotational dependent, and this allowed them to do something very practical for their work, which is to discard some data, because as the authors defend, a naive approach for them would be to try to gather all possible data in the situation, but that would be quite hard and very time consuming. So by making those assumptions, this allowed them to take into account only two information, which is eccentricity, again the distance, and spatial frequency. So this made their lives easier, probably. All right. So from the user study and the results that they got, basically we can highlight two main results. Okay, the user study, sorry, of course. Firstly, the user study itself was basically putting people in that display and see how they liked or preferred the image, depending on how they projected it, but also trying to understand where the light itself was reaching into the eye, etc., etc. From this, basically, they could define some thresholds for the flicker fusion, for what they call the CFF, the critical flicker fusion, which is basically the point in which after that you would not be able to recognize any changes in you would not recognize the flickering, so flicker fusion would basically happen, and light would be good. The image would be good. So why is that actually important? Because if you can find the which are the thresholds for this, we can then discard other frequencies. Because if you find that there's a range of frequencies in which we have a good image, but outside of these frequencies in another region of the fovea, it doesn't make really a difference for the user, we can then remove those frequencies and duplicate the image around those regions, so it's less machine demanding. All right, another result that we're going to analyze further is that this model could also be used for error metrics, better error metric for these circumstances, rather when compared to other already existing error metrics. So, right. So here we have the image with the analysis and different frequencies that they use for the image that they're displaying, and basically what we can understand from this color graphics is the following. Basically, where you see it brighter, more close to the yellow, is where the image is alright. It's good. And where the frequency is high. When you get to the darker parts, basically what this means, what those regions in the images mean, is that it doesn't actually make so much of a difference for the eye. So basically, when you get around those regions, the darker regions, the eye does not really perceive the image so good anyway. It's not that the image is bad itself, but it's that for the eye, you don't actually notice it. And another way of understanding this, to be more practical or relatable for you guys, is basically understanding that from how the human eye works. If you put your finger here, there's like some and go like to behind with your finger, there's a point where you cannot see your finger anymore, but also like there's a certain region where color is not really like distinguishable anymore. So this is very interesting because in this case it's not for color or for space, but for the frequency of the image. And this is very interesting. So because basically we can save on those bandwidths as was said before. Here for the error metrics actually, this user study basically they did it like a survey with the users, and this basically defined the DMOs. It's I forgot what it means, but basically this is the dynamic mean. I forgot what those four letters mean, but basically they get the opinion of the users and they make a mean value. So that's the DMOs. And here refers to the quality of the image. Here in red, you can see it's their prediction from their model. And those other three are other they call VKM, which is basically the quality of the image. So it's basically methods for inferring how good is the image. And we can see here that for the temporal aspect of the human vision, the graphics for their method is more close to what the user perceive. So it also shows that their model not only can be a foundation for further investigation and the development of methods for saving bandwidth, but it also gets closer to how users perceive the image in this aspect and can be used also as an error metric. All right, here's another finding that they did. They noticed that doesn't matter the pixel size, the pixel density, the improvements in compression of the image is still very good. And something else that we can gather from those graphics is actually this here. You can see that the blue one refers to only spatial savings, which refers to other video graphics techniques. And then here you have their techniques in different frequencies, of course. But basically, as you can see here, is that indeed, if you use only spatial savings or techniques that only consider spatial aspects or only the eccentricity or the equity of the image regarding eccentricity in the eye, if you add also the temporal aspect to it, you also gain compression even more. So this is promising. All right, so there are some limitations though. Of course, the first one, as we saw, they made some assumptions in the beginning. Those assumptions, of course, they add up to some expected limitations. So further investigation will have to be made to understand if the assumptions they made actually hide some more specific data regarding the gains that they noticed. Not only that, they didn't also account for the dynamics of ocular motion. So this is also another limitation. This is something that could add up for future research. And yeah, as we saw, the model was suggested by the authors to be used also as an error metric for this kind of context. And of course, its importance, it's very notable because it's basically a groundbreaking foundation for future work on that matter. So, any questions?
Yes, thank you very much. I have a few questions concerning the parameters as they took into account. So they are looking at the deviation from the fovea in degrees. That's one thing.
Okay.
I understood. Right?
Yeah. Yeah.
And so what else did they take into account? So they took probably the temporal flicker into account.
Yeah. The frequencies of the. Yeah.
But how did they do that? I mean, did they just look at the critical flicker frequency? So where you have alternating stimuli, and at some point you cannot distinguish between that anymore.
Okay.
Or maybe you can say a little bit about parameters they actually investigate.
All right. For specific parameters, they analyze those two things. Basically they would project. Let me go back. They project first of all in degrees. That degrees represent like the eccentricity, so it's like how far from the center it is. But it's degrees because you have to remember that it's a 3D actually, because it's not a circle, it's a sphere. So basically that's what they are doing here. So yes, this is the first parameter, and the second one is the frequency of the image they are projecting, and this frequency here. From what I understood of the article, I'm not so sure about it though, but from what I understood, it's basically this shows how each region of the fovea would react to the light, the image they're projecting. So I understand that this frequency here would be like how much stimuli is happening over time, something like this, I guess.
Yeah, I mean, flicker fusion means they are testing whether something is noticeable or not.
Yes.
I mean, in the case of the eccentricity, for example, it means that when you're rendering, for example, with a VR headset with eye tracking, then you can render with a high quality in the foveal area, and you can render with a lower quality on the peripheral area. But I mean, this depends on so many parameters. I mean, this also depends on whether there's a moving object in the periphery. It depends on the luminance that you have, whether it's a bright image or a dark image. And I'm not sure which kind of parameters they actually took into account here.
Yeah. Okay. The luminance actually they gather afterwards. The luminance they also took into account to see if there was if it showed some difference, if the model was still consistent regarding luminance, and they confirmed that it showed this consistency. For the moving objects, that's I believe that the part that did not consider, which represents one of the limitations, because they did not consider for the dynamics of the moving of the eye, and I don't know, something else that they did. They only used, if I'm not mistaken, the green color, the green channel to show the images, and yeah, yeah, it's I believe yes, like for sure, we need a lot of other informations and attributes to analyze this, and I believe that's what represents some of the limitations that the authors stated themselves. The fact that they didn't take into account so many attributes. I don't know if that answers.
Yeah, in a sense. I'm still entirely sure how they actually conducted the experiments. So, what did they show the participants?
Oh, it was. I don't remember for images or videos, but I believe it was videos. They showed them, I think, 8 or 11 videos.
And did they tell them to focus on anything specific, or were they allowed
Oh,
to do
yes.
whatever
They should notice like what was clear to them, what was not, like how good the image was, but also they would change like the frequencies of the videos, like for the frame rate, and then they would ask if they would notice any differences, and from this they would like reckon. Oh, okay. So if you change the frequency this way, then these regions of the videos become better or worse.
Okay, but that means they track the eye motion of the participants.
No, they only surveyed them, if I'm not mistaken.
So they didn't track the eye motion; they just showed them the videos.
Yes, because.
But how would they then come up with these angular measurements?
I don't know.
Yeah, I think they must have tracked the eye motion. Otherwise, it doesn't make sense.
Yeah, I agree with you, but I'm not so sure of that, specifically because they state that they did not take into account the dynamics of the eye motion. So I don't know if I wouldn't be sure to say that they did that.
It also means something else, that they didn't take into account that the eye is usually doing small stirrings, or
Oh, I see.
maybe they removed some of the frames after a saccade of the eye motion or something like that.
I see. Okay.
Right. Other
say, varied undulation frequency or stochasticity with respect to moving gaze position. So, there's the difference.
Right. Do we have any other questions? Okay, then let's thank the speaker again. And we're coming to the last talk of today, the realistic luminance in VR.
Should I leave it here?